Hello again. Okay, let's get started. So welcome to performance bugs and low-level Ruby observability APIs. And I would like to start with, good morning, Matsuyama. It's super exciting, and I feel super honored to be here to opening of the second day of RubyKaigi. Still so many talks to go, so let's get started. So who am I to be talking to you about this today? My name is Anjo. I'm originally from Portugal, and I'm a senior software engineer at Datadog. I work on the Datadog Ruby continuous profiler, and the reason I started doing that is that I really enjoy kind of making tools that allow us to look at our applications in many different and new ways and see what we can find out, what we can learn when we're doing that. If you haven't heard about my employer before, Datadog, we do modern monitoring and security as a service. And specifically for Ruby applications, that means that we have profiling, distributed tracing, test optimization, security, errors, logs. Here's a pretty screenshot showing a bunch of metrics and a bunch of information about different endpoints on the flow between microservices. Here's a pretty screenshot of the profiler, the product that I work on. And this is a flame graph showing where the performance is going for this application. And this is another screenshot of the profiler where I'm showing the timeline view, where basically we have a list of threads and you can see what every single thread is doing at any point in time. So with that said, thanks to my employer for sponsoring this trip. Let's talk about low-level Ruby observability APIs. And what do I mean when I say low-level Ruby observability APIs? By low-level, I mean APIs that are kind of close to the C Ruby VM implementation, to details that usually you don't need to know about, and it's even better to ignore them. But in some cases, when you're debugging hard issues or where you're trying to find out what exactly happened in some situation, it's a good thing to know a bit more about these things. This means that JRuby and Truffle Ruby will not kind of be included in this talk, but they do offer some amazing tools, and I'm super happy to talk about it any point in time. And, well, observability APIs, which is the idea is that they allow you to X-ray what and how your application is running. What's it doing exactly, and why is it doing it? OK, so, but why? I like to think of the how would you know problem, which goes a bit like, OK, if your tests are passing and the app returns the right result, but it takes 5 seconds to return the result, how would you know if maybe you have an n+1 query problem? You're going way more often to the database than you think you're going, accidentally. Or maybe your service is perfect, but it's slow because a different service is slow. It just keeps waiting for the other service, and your service has done nothing wrong. It's perfect. No bugs. How would you know if there's some background thread that's using up a bunch of CPU and basically adding latency to your requests? How would you know if the Ruby garbage collector is having to collect a lot of objects, and so it's kind of adding a bunch of latency to your application? And well, yeah, the idea is that you can use Ruby's observability APIs to understand what's going on. Or more commonly, tools that you build using these APIs, which is the topic of this talk. You can also use a lot of put-tests, and shout out to Aaron. We are all big put-test debuggers. It's the best debugger when you have nothing else. But sometimes some of these observability APIs give you a bit more. OK, so observability also helps with the problem if your tests are passing and the app returns the right result in staging, but breaks in production. So it can give you a lot of information on a lot of different things. There's also a related problem that I like to think about, which is the Ruby is slow, and I need more air quotes, lots of air quotes, Ruby is slow problem. Which is you build something and it doesn't go as fast as possible, and you're OK, obviously this is not going faster because Ruby is slow. It's not that the service maybe is doing n+1 queries and you didn't figure that out, or that there's some connection pool that was not configured correctly and a bunch of threads are waiting on it. or the service is using too many threads, and you need to kind of configure it a bit differently and use a bit more Ruby processes, etc. So, like Ruby is not slow. It's just we should learn why our applications are taking time, and if we learn about that, we can actually fix them. And Ruby is really fast. You might have thought about, okay, there's a lot of existing tools. The Datadog Continuous Profiler, StackProf, Vernier, JVL tools, Bybug, etc. And the really cool thing about these tools is that all of them are based on the APIs that we're going to be discussing today. And the thing I find really interesting is that the different combinations of the APIs that we're going to talk about today create very different tools. So you use this API, and you get a debugger. But if you use this API and this API, you get a profiler. And it's kind of very interesting to see that all of these tools are very close to each other, and they are all accessing very similar kinds of information. And so it's very cool to see the underpinnings, what's beneath these tools. How are they doing their magic? And I also want to see new and interesting combinations. Maybe people have tried this API and this API, but no one tried this one and this one. So I really want to see what other things we could be building, what other ways we could be looking at our applications. And as well, maybe there's things that can be added. Maybe there's things that can be improved. Maybe there's things that right now we can't see in Ruby, but we would like to. So let's get that conversation started, and let's improve those APIs. OK, with this said, let's look at what Ruby offers and what problems we can investigate with it. So where the magic happens, today we'll be focusing at kind of two files in Ruby. This file, debug.h, that offers the tracepoint APIs. It offers the postponed job API, the frame profiling APIs, the debug inspector APIs. And then there's another file that I want to kind of steal a couple more points from, which is a thread.h file, which offers the JVL instrumentation API and the thread-specific storage APIs. So, yes, I will be showing some C code today. I'm sorry in advance. And but to make it easier, I have kind of created a new gem called Low-Level Toolkit. And I will be using this gem to give you an example of how to use these APIs. And the whole idea of this gem is to be two things at once. It's going to, I'm hoping to make it a repository of a lot of very small tools that you can use to investigate applications. But it's also a living example of how you can use these APIs. So if you want to use them, you want to experiment them, instead of having to start from scratch and figure out how you build some C code and how you do that, you can just clone this repository and start using it and playing with it. OK, so let's talk about the tracepoint APIs. And the first thing you might start thinking when I say tracepoint APIs is, wait, doesn't Ruby already have the tracepoint class? It's right there in the documentation, a really great documentation, a really amazing tool. And yes, that's the answer. You can use Ruby, the tracepoint class, with all of these events. You can use it to figure out when a method gets called, when a method returns, when a class gets defined, when an exception gets raised, etc. from Ruby code. But there is a bit more about the tracepoints, is that there are a few more special events that are the internal tracepoint events. And you can really only use these internal events from C code. So you cannot use these events using the regular Ruby tracepoint class in your code. Obviously, the C code can still use all other events. So basically, C code has a bit more of an advantage here because it can use the other events and it can use these events. And the thing about these internal events is that they are separate because they are emitted at very special situations where it's not possible to access many Ruby APIs. And I'm guessing this is why they are not wired up to the regular tracepoint Ruby class. It's because it would be really hard to do that. So let's look at a few of these events and what cool things we can do with them. So the first one is let's look at investigation object allocation, the new object event. It can be used to answer questions such as, are my application's web requests delayed by GC? Because you can use it to look at objects that are being created. And because if you are creating too many objects, this gets expensive for two reasons. One is that creating many objects uses up CPU. You're doing a lot of work to create those objects. And then a bit of time after that is that Ruby will have to clean up all of those objects as they become garbage. So when you create a lot of objects, you kind of add overhead in two places, in creating the objects and in collecting all of those objects with the garbage collection. So let's build like a tool to investigate object allocation using the new object event. Specifically this tool, the track objects created tool. And the track objects created tool basically executes a block, and then at the end returns all of the objects that were created inside the block. And you'll see here that object.new and hello world are directly created like inside this block, but the time object actually gets created inside the UTC method. So this is basically telling me all of the objects that got created, even in other methods that are getting called from this code. So how can we build this very simple tool with the track objects, with the new object event? Okay, this is where the C code comes in. So we create like this track objects created function in C, and this is how you create a trace point from C code. So you see RB trace point new, it's the equivalent of what you would do in Ruby. But now you can pass the special event, which is the new object event, which is one of those events that are not available to Ruby code. And then we pass a function on new object event, which is the function that Ruby is going to call when a new object gets created. And then there's a bit more boilerplate. We have to call a function to enable the trace point. Then we call RB yield to yield back to Ruby and run the block. And then when Ruby returns, we disable the trace point, and we have to do that filter hidden objects that I will explain in a bit. So the next part is the on new object event. So when a new object gets created, Ruby calls this function. And what this function does is it gets the object that was created. And if the object is not an internal object, then it adds it to an array. As simple as this. I will explain a bit what the internal objects are in this case. OK, so this is one. So we are basically adding all of the objects that get created into our array. And then the filter hidden objects is like an extra step that we do at the end, where we again go through, like this is just a loop. So we're going through every object that we collected. And we are checking if the object still has a class set. And if the object doesn't have a class set, then we kind of replace that with a nil. And this is because the objects that don't have the class set are hidden, and I will explain a bit what this means. And that's it. Like, this is all we needed to implement track objects created. And we can now investigate in like a given piece of code what are all the objects that got created and what are those objects. And an interesting thing that you see is that because we are collecting all of the objects that got created, whereas you would expect like object.new and time and etc. to be garbage collected, in this case we're actually holding references to them so they don't get garbage collected. So we can look at them later. Okay, things to keep in mind when you are using this kind of event. The one is that the objects are empty when the function gets called. So when Ruby calls your function, Ruby gives you the object. But if you try to look at the object, you will see nothing, because the Ruby calls you just after locating the object, so before initialize got called. So it means that if you'd like to say, oh, I wanted to see what the value of this variable or whatever was in the object, you can't, because the object is still empty. Furthermore, you cannot call into most Ruby APIs inside this callback. So even like you might want to try to do a few things, but you need to be careful, because most Ruby APIs, you cannot call them in this situation. And if you do, it leads to very confusing crashes. And well, ask me how I know that it leads to very confusing crashes. And yes, be careful about internal and hidden objects, which is why you saw like two different filters. You saw me filter if an object was internal, and you saw me filter if an object was hidden, and those objects I am not returning back to Ruby code. So let's talk about that. Internal and hidden objects. Did you know that Ruby actually itself, the Ruby VM, uses objects to keep like internal details for itself? And this can be caches, this can be metadata, such as like the information on the method, or even like the bytecodes. included modules, etc. So Ruby has like special objects that it uses to keep its own things, but these are regular objects that the garbage collector also kind of controls and scans and whatnot. And even you can see them sometimes. Like for instance, if you call object_space.countObjects, you'll see like a breakdown of different kinds of objects that Ruby is tracking. And at the bottom, you'll see iMemo and iClass. And these are like some of these internal objects that you don't usually see. And the Ruby usually the reason why you might not even know that these objects exist is that all Ruby APIs hide these objects from you. So you're never supposed to get an instance of this object going back to your Ruby code. And that's why we were kind of removing those objects, the internal and the hidden objects from our tracking, because we shouldn't return them back to Ruby code, because sometimes that causes crashes and issues because, again, they're not supposed to go back to Ruby code. But they exist. And these low-level APIs show them. So this is kind of a pattern with the low-level APIs, which is, well, when you're very close to what Ruby is doing, sometimes you're seeing some of the magic under the hood, and sometimes you need to collaborate with Ruby so that you don't break the rules. But sometimes you can bend them. OK. So let's look at a few more events. The garbage collector activity. The garbage collection events are really cool to answer questions such as, when is garbage collection happening? And there's a bunch of events related to different garbage collection events. When Ruby starts, when Ruby finishes, when different stages of garbage collection finished. And this is obviously useful if you're kind of trying to understand the activity of the garbage collector in Ruby. Like, why is the garbage collector kicking in now? What's happening in my application? And if you've used gc.stat from Ruby code that gives you a lot of metrics, you can kind of think about this is like gc.stat ++. So it gives you a few more things. You can experiment and get a bit more information that gc.stat does not give you. So let me give you an example. Let's build this print GC timing tool. The print GC timing tool, what it does is, well, we create a new trace point, and it will hook on the GC enter and GC exit events. So we're looking for when a GC starts and when a GC finishes. And then we ask Ruby to call our onGC event function. And in our onGC event function, what we do is, when we get called, we need to figure out, OK, which event are we talking about? Is it start or is it exit? If it's start, what we do is, enter, what we do is we get the current time. So basically, I've created this very tiny helper function that kind of gives, it's the equivalent of time.now. But what's the current time? We store this current time. And then when the garbage collection finishes, we get the time again. We subtract the current time with the time of start. And we can print how much time the GC took. And in this case, we're printing this directly to the standard output. So basically, whenever garbage collector will run, we'll get a very simple print saying OK, the garbage collector ran, and it took this amount of time. And that's it. This is all we needed to build the print GC timing tiny tool. And here I'm explicitly telling Ruby to do a GC, both a minor and a major, and then we see that we get the output that we wanted in this case. And you will also see that, kind of as expected, minor GCs are much faster and to execute, and then a major GC actually takes longer. But still, 2 milliseconds, that's pretty fast. But yeah, ideally, this is why you want to avoid having many major GCs in your application. And ideally, you'd want to have Ruby just kind of do minor GCs most of the time. And so yes, sorry, next slide. So things to keep in mind when you're doing this work around the GC APIs. You cannot allocate any objects, which, well, if you think about it, somewhere in the Ruby code, you're trying to create an object. And when you're going to create an object, Ruby looks at it and thinks, oh, there's no space. I need to do a garbage collection. And then Ruby starts doing a garbage collection. And then Ruby will call into your code. And what will happen if you allocated an object? it would kind of start the cycle again, like, oh, I need to allocate an object, I need to do garbage collection. It will not be very good. So you cannot do this, and actually Ruby will immediately stop, will kind of say, nope, nope, you're doing this wrong. So this is very helpful, but yes, obviously it means you need to be a bit careful when you're writing this kind of tool to not allocate any objects. And also, you cannot call into most Ruby APIs inside this callback because, again, most Ruby APIs, often they need to create objects, so kind of this would happen. Okay, before we talk about the other APIs, I will kind of suggest that if you're doing things around trace point and performance, you might want to look at the bottom of debug.h where this event hook thing comes. Because, hint, hint, the trace point in Ruby is actually built atop the low-level event hook API. And if you're trying to build a trace point that gets executed very often and you want to make it go faster, this one is kind of slightly less overhead, or at least can be made to be slightly less overhead. So you might want to take a look at these undocumented advanced tracing APIs if it's something that you're interested in. Okay, let's talk about the postponed job APIs, which is a very interesting API. So the postponed job API kind of looks like this. There's a pre-register function and then a trigger function. And the idea of the postponed job API is to ask Ruby to run code safely or at a safe point. And if you haven't heard the term safe point, well, it's not surprising because Ruby doesn't actually call it a safe point. The term safe point comes from like a bunch of other languages. It's used in Java, Go, .NET, Truffle. And it just means like a moment in execution of the code where it's safe to perform certain operations. So like when you're thinking of the Ruby VM, sometimes it's kind of in the middle of doing a bunch of things and doing GC and doing whatever. And like it's not always safe to just like run Ruby code there. And this is kind of what we mean by a safe point. In the case of the Ruby VM, again, like it means that we can get called when it's safe to call into Ruby code, when the JVL is being held, not in the middle of GC, allocations, etc. So why would you want this thing? Well, the thing is that like you've kind of saw in the when I was talking about the trace points that I was saying, oh yeah, in low-level APIs, it's very common that I will say, oh, you cannot create any objects when you get called in these APIs. You can't call into methods written in Ruby code. You can't call most VM APIs. And you might not even have the global VM lock when Ruby kind of calls your low-level thing. So the idea of the postponed job APIs is to kind of create a bridge between those APIs and doing some of the things that you couldn't. It's a way of saying to Ruby, hey, Ruby, when you have a moment, like, can you call this? I know that now you might be busy, but like when you are a bit like chill, call this. And so it's a way of doing a lot more things from the low-level APIs that you wouldn't otherwise be able to do. And well, let me give you an example. So before, you saw me doing a very simple tool that would print whenever a garbage collection happened. And you might not have noted that I did something on purpose. I did my printing using C code. I told like C code to actually print directly. Because if I tried to use any Ruby code to do the printing, it wouldn't work because I can't call Ruby code. So what if we wanted to do something like this? We have the onGCFinish, and onGCFinish gets a lambda, and our lambda will actually print when the GC finishes, and will also print the kind of GC. And here, again, we're like running two different kinds of GC, and we want this kind of to be the output. How can we build this using the postponed job APIs? Well, what we'll do is we start by pre-registering like a callback. Our callback is called postponed in this situation. So we kind of tell Ruby, okay, at some point in the future, I will want to call this. And then we build our onGCFinish, where we save the block or the lambda that the user got called us with. And then we create a new trace point with the GC exit event. And then when the exit event happens, so when GC finishes, instead of like immediately printing, what we do is we tell Ruby, okay, we're ready, please trigger the postponed job. And then in the postponed job, we are now able to call into Ruby code. So we do this at the bottom, which is just we take the callback and we call on it. So we call on the lambda that we get, and that's it. This is all that we needed to build this like variant of our tool that now can call into a Ruby block whenever GC finishes. So this is why the postponed job API is really interesting, because we kind of can use it to bridge back to Ruby code and to do things that otherwise would be hard to do. Okay, so things to keep in mind when you use the postponed jobs API. This API actually got it became very different in Ruby 3.3, so it got redesigned. And so if you want to use it on an older Ruby, it's still there, but basically what happened was we found out that there's like a very difficult to solve design problem in the old version of the API, and that's why the API got redesigned. So if you want to use with older Rubies, you still can, but you need to take into account that you might be hit by this problem. And the other thing is that when you call trigger, the trigger flag is thread local, which means that if you call it from a background thread, it might not work as you expect. So you might want to experiment a bit and read a bit into how to use that correctly. The other thing to keep in mind is that there is a limit of 32 different postponed jobs that can be registered, and no more after that. There is no garbage collection. There is no removing postponed jobs. So it's like you register 32, and that's it. You need to restart Ruby if you want to change your mind. And actually, the Ruby garbage collector already uses 1. So actually, we only get 31. So try not to use too many in your application, because you might want to use a gem that uses 1 or 2, and then, well, you have a limit. The other final thing to keep in mind is save point bias. And this is a term that also comes from Java and some of the other runtimes, which means that basically the next save point, so when you call trigger, usually Ruby is pretty fast in running your code, but it might still call into the next method or return from a method before it actually calls the thing that you've asked Ruby to do. So the next save point might actually be in a different method. And this is often important for profilers or some tools that, okay, if you're looking at the current method might have changed by the time that the save point gets executed. Okay, let's go to the next one, the frame profiling APIs. And, well, there's a bunch of them, but basically the two ones at the top give you the current backtrace, and then the ones at the bottom are just the C functions to get the information from the backtrace. And so this allows you to get the backtrace both cheaply and safely, and answer questions such as, well, what methods are being called and where? So you will not be very surprised when I tell you that this is the source of many pretty profilers that use this to build beautiful flame graphs of what's going on in your application. And an exception, I would say, if you were here for the SDB profiler session yesterday, well, SDB does not use these APIs, which is the big key point of SDB. But a lot of the other Ruby profilers use these APIs. And why they use them? Because these APIs are really useful, because they give you a backtrace without allocating new objects or calling into Ruby code. And again, if you think back to the things I was saying before, where I say, you cannot create new objects, you cannot call into Ruby code in some of the other APIs, this API is kind of built to kind of connect very easily with that, because it doesn't need to create any objects. And this also makes it very, very cheap, which is good for profilers, because you don't want your profiler to make your application even slower. And it can even be used in a signal handler. So this is what's called a sync signal save function. Although I think it's not officially documented as one yet, but that's kind of the intention. And that's how everyone is using it most of the time. And so yeah, it's very similar to getting backtrace locations. So if you've used backtrace locations, it's basically the thing, but it's designed to be used with the other low-level APIs that we've looked at, and it's cheaper than backtrace locations because, well, it's for profilers. So let me give you an example. Let's try to build this thing, the last allocation at. So inside this block, when we call track last allocation at, we can call a bunch of code, and here we're just calling into the hello method. And when we call last allocation at, what we get is we'll get the stack trace of when the last object got created. So in this case, we see that the object got created inside the hello method because it was that object that you see over there. So this is kind of like, oh, you want to investigate where objects are getting created. And OK, let's build this helper. So we start with our track last allocation at that we saw being called from Ruby. And again, we're using a trace point, and now we're using the new object event, so you can see how these things connect. And when the new object gets called, what we do is we check if it's an internal object. If it's an internal object, we don't want to touch it, ignore it. If not, what we do is we create like this temporary buffer. And this buffer is created like this is C code, so it's not like an allocation. And then we call RB profile frames to get the backtrace. And then what we do is we kind of copy the backtrace to a temporary Ruby array that I've created at the top, so that we can access it later. And then when you call last allocation at to be able to ask the question, OK, where was the last allocation at? We have to use a small trick to pause the recording of the information, because the one thing we want to do is like we want to create a new array. And, well, you don't want to, when you create a new array, then the last object was your new array. So you kind of do that. And then what we do is we kind of copy, we ask Ruby, OK, what's the file name? What's the method name? And we copy them into this new array. And then we return this information and resume recording again. And that's it. That's all we need to build like a helper such as this last allocation at. And the really cool thing about this helper is that you saw that whenever a new object gets created, we do very, very, very little work. And so keeping this enabled will not impact your application a lot. So this is the kind of thing why this API is useful. And in particular, it will not create a lot of objects, so it will not add more work to the Ruby garbage collector. Because otherwise, if you think about it, if every time you create one Ruby object, then you will create 10 more to record the information about creating the Ruby object, then this becomes a problem because, well, suddenly you're creating 10 times more objects or 20 times more objects than you should. So that is why this is useful. OK, things to keep in mind when you use this kind of thing. If you store the values you get from Ruby in a C data structure, you remember that you need to tell the Ruby GC about it. And this is like a general thing from every like Ruby native C extension. But it's a hard thing. It's like hard to forget. It's like easy to do. Oh, I'll just add this here, and I forgot to tell the Ruby garbage collector about it, and you will create problems with it. OK, let's talk about the debug inspector APIs. And the debug inspector APIs give you like a nice way to navigate the current active backtrace and methods. And so you might be like, if you're paying attention, you might be thinking, well, wait. Backtraces again? Didn't we just like, wasn't the previous one like the whole thing about backtraces? Why do we need a second API to do backtraces? And the answer is that the debug inspector is way more expensive than frame profiling. So again, like this is the reverse. What I was saying, the frame profiling is like no object allocation, it's very fast, etc. This one is actually does object allocations, and it's kind of slow. And that's why it's not very often used by profilers. And it also needs to call into Ruby code, etc. So it has a bunch more restrictions. So why is it useful? It's useful because it's built for a very different use case. It's built for debuggers. And the key thing about the debug inspector is that it allows you to go deeper than any other backtrace API allows in Ruby. So whereas the previous API, I was saying, oh, this is the same thing as backtrace locations, the debug inspector is not the same thing as backtrace locations. It's much more powerful. It allows you to access the objects that methods are getting called on. It allows you to access the binding objects for those calls that are happening, which means you can read and change arguments from those calls. You can read and change local variables, etc. You can even access the instruction sequences, and you can then ask Ruby, OK, print the bytecode of the method that's getting called, like still here on the stack. So this is the debug inspector. It goes much deeper. So let me give you an example. I'll jump directly to C code, and I will say I will build two helpers. the who called me helper and the who called me binding. And the idea of this is like who called me is like when you call it from a Ruby code, it will give you the object that called you. And the who called me binding, it's like the binding of the object that called you. And we do this by calling debug inspector open. And then inside our callback in debug inspector, we basically, if we ask for the who called me, we use RB debug inspector frame self get. If we ask for the binding, we get debug inspector frame binding get. And then the depth, the idea of the depth is that like the current method when we call the current one, like depth 0 is us, and then 1 is the caller, and then we want the caller of our caller, so we need to ask for depth 2, and that's why the 2 is there. But this is a bit abstract, so let me show you what cool things you can do with this. Imagine you have this very simple hello class. And when you call say hello, you pass it a to object, which hello will call hello on. And there's a secret. And the idea is the secret is that like the secret is an argument, so it's just there. Like nobody can see the secret. And then we create the spy object. And the spy object implements hello exclamation mark. And it uses the who called me and who called me binding to actually access the secret and see what object called it and what the value of the secret was. And so when we create a new instance of hello and we tell it to say hello to the spy and then we give it like a secret, trust no one, actually the spy is able to say, this is the object that called me and this is the secret of the object. And you can see how like otherwise this would never be something that you could do in Ruby. So things to keep in mind when you're using the debug inspector. There's already gems for this. So actually, if you use the binding of caller gems or the debug inspector gems, they basically already, the whole thing that these gems do is give you access to the debug inspector from Ruby code. So you don't actually need to write C code to use the debug inspector. But this is a really powerful thing that you cannot do in any other way in Ruby. OK. Let's go on to the last one, the JVL, or Global VM Lock Instrumentation API. And wait, if you haven't kind of, I've done a few presentations in the past about the JVL, but if you skip my presentations and you go like, what's this JVL thing again? Here's the Global VM Lock explained in one slide. It's similar to the Python GIL, the Global Interpreter Lock. It's just, we call it differently on Ruby. It's something inside the Ruby VM that protects the VM state. It's actually not global anymore. If you're using multiple reactors, you will have multiple JVLs. But if you're not using reactors in your application, you will only have one. So you're back to kind of having one. And it prevents Ruby code execution parallelism. So it means that multiple Ruby threads cannot be executing Ruby code in parallel at the same time. But waiting can happen in parallel. So if you're doing a bunch of like calls to the database and a bunch of network calls, this is fine. The JVL only prevents running multiple threads of Ruby code at the same time. And this means that like the JVL can impact your application latency if you have multiple threads that are trying to, that need it to work at the same time. So this is the context of the JVL instrumentation API, is to be able to know more about the global VM lock. And you basically get a bunch of events that we can subscribe to, and then there's an API to subscribe to this event. So it's kind of similar to TracePoint, but it's not called TracePoint. It's slightly different. And so this API allows you to track Ruby thread activity. And so you can answer questions such as, are my web requests being delayed by other requests or other threads in general? So it allows you to know when threads are running, which Ruby calls resumed, or waiting for something to happen, which it's called the suspend event, or want the JVL, which means ready. And at the top, you see a screenshot from the JVL instrumentation gem, which is like a gem that I created where it kind of gets this information from the JVL instrumentation API and just generates it in like a visual timeline. But this is the kind of information that you get from this API. Without this API, this gem could not exist. So let's see what we can use, what we can do when we use this API directly. Let's say that, for instance, we have a Ruby method that just kind of uses up a bunch of CPU by incrementing a counter in a loop. And then let's build a track once JVL helper, in which what we're going to do is we create 2 threads. Each of them is going to run that loop. And then we join the threads. And then at the end, what we'll want to know is like how much time those threads spent waiting for the global VM lock. So to do that, let's build track once JVL. We create the add event we call add event hook. We say that we're interested in the started, ready, and resumed event. And we want Ruby to call us on our onThread event function. And then inside onThread event, we get the information of the current thread. If the thread got started, we do some bookkeeping. And I will tell you a secret, is that actually the way I did it in the gem right now, it's technically not completely safe. So I kind of, I need to fix that. So imagine that is very safe right now. And when there's a ready event, which means that the thread wants the JVL, what we do is we store the information in like a thread local variable. So there's this API, the internal thread specific set, where, that is very useful to get like thread local APIs in from C code. So we basically say we get the current time and we record, okay, this thread started to set that it wanted the JVL at this point in time. And then when the thread resumes, which means the thread is finally, it gets the JVL and can run, what we do is, well, we get the time that the thread started waiting, we get also the total time the thread has spent waiting, and we basically kind of add that and store all that information in thread local. So there's a bunch of boilerplate C code, and this is the problem with C code. Like, if you did this with Ruby code, it would be like, I don't know, like 3 lines of Ruby code, and it would be very beautiful. But in C code, there's always more code. But yeah, basically, I'm reading the two thread local variables, and I'm storing the result in the total value. And then this is all that's needed. So what we do is we call the track once JVL. And at the end, we get a list of threads and how much time those threads spent waiting for the JVL. Here, the result is in nanoseconds, but I'm converting it to seconds because, well, it's much nicer to read. And let's print this. And here's the result. We can actually see that these 2 threads, they each run for some time, but they both needed to wait 1.8 seconds to be for the JVL. So basically, in total, this took 3.71 seconds, but both threads had to wait for a bunch of time because they were kind of fighting for the JVL. Okay, so things to keep in mind when you use this API. The resumed event, only the resumed event gets called with the JVL being held. For all of the others, you cannot call into Ruby API, so postponed job is your friend. And it's this internal thread-specific API is very useful to do this kind of thing where you want to record information inside the thread itself. And yes, I'm glad this API got added because before it was very hard to do this. And also, if you want this kind of information as a metric, as I was showing you in our example, the JVL tools gem already offers a lot of nice counters. But maybe there's a counter that it doesn't offer yet, and you want to experiment a bit, so you can experiment. And maybe you can then open a PR on JVL tools. OK, so you saw a bunch of things, a bunch of like very small things. So you might be convinced now that it's very easy to build very small utilities. But let's put all of the things we've learned together and let's build an actual new profiler in the time that we have left in this presentation. I can do that. So let's build a new kind of Ruby profiler that I don't think anyone has built before, which is a release JVL profiler. And what is a release JVL profiler? A release JVL profiler is a profiler that answers the question, when is the JVL being explicitly released in our application? And the global VM lock gets explicitly released when Ruby is about to doing like some network calls, or it's about to do some operation on files, or you're going to like the database using a native database driver. So we're going to get information about this. Plus, when native dev wants to do a bunch of work, it may also release the JVL. So we want to see where all of these points are happening in our application. And by knowing when the JVL gets released, we can see the impact of this, which is basically also places in our application where Ruby will switch away from the current thread. So if you have multiple requests, you might go from the current request to another one because, well, Ruby has released the JVL. And here's an example of some code that we want to profile with our release JVL profiler. This code actually gets the counter loop again, and then it does like a network call to get the Google front page. It reads like a very big file. It lists the file, which files are inside that directory with dir.children, and it also does a bit of compression of the big file that we read. And this is the result. Like, this is a beautiful flame graph that I've generated using our new release JVL profiler. And you can kind of see that there on the left, we see the multiple kind of things where Ruby is doing work to read the Google homepage. So we can see like multiple stacks and multiple things that Ruby need to do for that. We can also see there where Ruby is calling io.read to read from the file. And you can also see there where Ruby is compressing the file and releases the JVL. So, and here you see at the top where the width of the flame graph represents time. So how much time our very simple application took with the JVL being released. What you might not see is like the counter loop does not show there because the counter loop never releases the JVL. Ruby might take away the JVL from this thread, but the code never explicitly releases the JVL. And you might not have seen like the listing of the directory, which is because like listing directories, it's very fast operation. But if we switch our profiler from time to count or how many times the JVL got released, actually it shows up very quickly that the dir.children actually released the JVL 180 times. And I checked 180 times is the number of files I had in that directory. So basically, Ruby will release the JVL once for every file that's in that directory. OK, let's build our release JVL profiler. Before we do that, I will say it's often surprisingly easy to generate the output in a format that can be visualized using existing UI tools. So in that example you saw here, I'm using the speedscope.app website, and it's very easy to generate output to like this kind of tools: Speedscope, Perfetto, Firefox Profiler, sometimes even Excel. So pro tip, sometimes you're looking at the data and you just have like a big text file with a bunch of like outputs. Try to see if you can generate in a format that can be loaded in a tool, because it's often very useful to look at that data using a UI tool. Okay, so part number one, when you call release JVL profiler, we add the internal event hook. We're using the JVL instrumentation API, and we want to hear about suspended and resumed threads. And then we have the usual boilerplate. We yield back to Ruby code, and then at the end we kind of stop the event hook, and then we will do some work to write the output to the format that Speedscope needs. Okay, second part. When there's an event and we're looking for the event suspended, and that magic Ruby thread has JVLP function. I hadn't talked about that one before, but basically it tells you if the thread explicitly released the JVL or not. So this is how we can tell when like a thread actually said like, oh, I want to release the JVL because I want to do something without the JVL. And what we do, well, again, we just record the current timestamp so we can use it later. And then later, when the thread is able to resume again, we read the time in which it kind of released the JVL. And then we get the current backtrace. And here, I'm not using the profile frames API. I'm not using the debug inspector API. I'm using the RB make backtrace. Why? Because it's shorter to fit in the slides in this case. But again, like if you wanted to make this profiler like lower overhead, you could use RB profile frames. If you wanted to make this profiler get more information, you could use the debug inspector. So that's the idea of these different APIs existing. It's like for different use cases. My use cases here is like make it easier to fit in the slides. And what I'm doing is I have a Ruby hash and I'm recording for every stack trace. I record some information. So I first check if I already have information. If not, I initialize with zeros. And if I do, what I do is like basically I count the time spent without the JVL. And at the bottom, you see basically I keep two counters. I keep a counter which is like how much time we spent without the JVL, and a counter which is like how many times we release the JVL. So we can create the two kinds of profiles that I was showing you, the count and the time profile. And then that's it. The only thing we need to do is to write the stacks in a format that Speedscope understands. And this is like a lot of boilerplate, and I will admit that I've kind of simplified this. But basically, we're going through the hash with the information that we recorded. We have to print out the stack trace that we got, and then we print the counters that we recorded. And this is the result. This is how it looks. It's basically two text files. At the top, you see a text file with the counts. So we kind of record the stack trace, and then 180 times in dir.children. And then at the other file is, OK, we recorded the stack trace, and then the time in nanoseconds that we spent. And that's it. We built a full new profiler in 107 lines of code, and I almost made it fit in 3 slides. So before I go, let me switch gears a bit and talk about performance bugs. And yes, this is the, I'm not sure if this counts as this being like another talk about profilers in RubyKaigi. So if that counts, this year we had 3 talks about profiler again. If not, maybe it's like 2.5 talks about profilers at RubyKaigi. Let's talk about performance bugs. So are performance bugs really bugs? Like if something takes 10 seconds but then gives you the right result, is it a bug? What if it takes 1 hour? Is it a bug? If it takes 1 day, 1 week? So like performance bugs, like sometimes people call them problems or issues, but in a way they are usually about resources. They're about how much X you use to give back an answer, which might still be a correct answer. It might be about like how much CPU you need to use to give an answer. It might be about how much memory you need to give an answer. It might be how much time you take to give that answer. And obviously, if you run out of that resource, if you run out of CPU time, wherever, then you might crash the application. So, but the key thing to think about them is to think about impact and thus their priority. So when thinking about this, you should kind of think about like, is this performance bug breaking production? How is this affecting the user experience? Will this take down our site on Black Friday? Is this costing us a lot of money? And kind of, if any of these are true, then you should usually go and like, let's fix this. We should fix this. And if you're not sure how to answer these questions, like observability tools can help you answer these questions of what's the impact of this problem, and also where is this problem coming from. So this is the tools that we looked at today that you can build using Ruby's APIs. But like in cases where none of these are true, I would say use your best judgment. Like sometimes we have the impulse to kind of optimize something. But sometimes that something does not need to be optimized, and we could do other things. So use your best judgment. OK. I am very excited to see what tools you will build with debug.h and what bending of rules and things you shouldn't be doing you will do with the knowledge you've learned today. And I'm very looking forward to seeing observability tools on stage during this and future RubyKaigis. And thank you. That was my presentation.